Starting any of the examples we've looked at before has been relatively straightforward. We were either given the specific function that we wanted to maximize, or we were given a model that would lead us to that other function. So for instance, we're given a price demand function, we can use that to find revenue. Or we're given revenue and cost, we can use that to find profit. Last two examples we want to take a look at are types of problems where we're not given that model. We're just given some information. From there, we need to actually construct the model for the function that we want to maximize, and then look at coming up with our actual answers to the problem. So in example 6, we want to find two numbers whose sum is 25 and whose product is a maximum. So the first thing we want to think about doing is taking this expression, two numbers whose sum is 25, and turning that into an algebraic expression. So we need two different numbers, so we need x and y, because we want their sum. So the sum of those two numbers needs to be 25. What we want to do is find their product to be a maximum. So that means we want to maximize a new function that we're creating, f of x, which is the product of those two values. Now we have a problem here that our function has two different variables. So in order to rewrite that in terms of just a single variable, we can go back to this first equation we set up and solve it for either x or y. In this case, we can solve it for y to get y equals 25 minus x. So instead of maximizing x times y, we can maximize x times the quantity 25 minus x. So we're still taking the product of those two values. We've just rewritten the second variable in terms of the first. So maximizing this function gives us a value of x to be 25 halves, or if we get the approximate form, 12.5. So we get our maximum function value when x equals 12.5 and y equals 25 minus 12.5. So we're coming back to this expression for y. In this case is also exactly 12.5. So we had to construct the equations that we needed to actually maximize. But once we have that function to maximize, the process is similar from there, using Wolfram Alpha to maximize, and then if the question were to ask for any interpretation, providing an interpretation. In example 7, we have something slightly more complicated. On a certain route, regional airline carries 6,400 passengers, each paying $50. They want to increase rates, but for each dollar they increase the fare, they estimate that they'll lose 80 passengers. So we want to let x be the number of passengers. So what we're told is that initially we have 6,400 passengers, and p be the price that they pay. So x is our independent variable, p is our dependent variable. So when we have 6,400 passengers, they're each paying $50. So we can put those together as a coordinate pair. Now what they're saying is if we increase the price by $1, meaning if we increase the price to $51, we would lose 80 passengers or only have 6,320 passengers. So using that information, we can plug that into the slope equation, taking the difference of our y coordinates, or in this case our p coordinates, divided by the difference of our x coordinates. And getting a result of negative 1 over 80. So now we can set up something in that general slope-intercept form. So y equals mx plus b. In this case we have negative 1 over 80 as our slope. So we have y equals negative 1 over 80, x plus b. We could replace y with p in this case, just for that consistency of the variables. So what we'll do is plug in either of our values for p. So we could go with 50, and that's going to be equal to negative 1 over 80 times that corresponding x coordinate, which would be 6,400, plus some intercept b. So solving for b would tell us that b equals 130. So we get a price-demand equation, which is going to be p of x equals negative 1 over 80x plus 130. From there, we want to find our revenue function, which is again just x times p. So we would get negative 1 over 80 x squared plus 130x. Using Wolfram alpha, we could plug in this function, ask it to maximize it, which should give us a result of 5,200. So the airline will achieve a maximum monthly revenue of, in this case, it would be 338,000 by selling 5,200 tickets for $65 each. So Wolfram alpha would output this x value for us, as well as this corresponding function value, which is our revenue function evaluated at 5,200. And then we would get the price of $65 by going back to that price demand function and evaluating it at 5,200. So at 5,200, we get a price point of $65 per ticket, which again is giving us that optimal revenue, number of tickets, and price point.